Before you start any section in math, you should always take a minute and read the introduction to the chapter or to the section so that you have an idea of what and why you're studying this type of mathematics. In section 4.5 starts on page 236, and you can read that paragraph, and it gives a little introduction as to why mathematicians or anybody really would like to ever practice using trig identities and why they're useful. Today, though, I'm just going to show you how to prove trig identities, because that's what you're doing. You're proving trig identities. And to prove an identity, you're showing that one side of the equation is the same as the other side. Okay, so you start by writing down left side of the equation, so you use LS, and you're trying to prove that it is equivalent to the right side of the equation. So you actually can't balance the equation. You can't bring one term over the equal sign like you are when you're solving. In this case, you're working specifically with the left side, then you're working with the right side, and you're showing that they are an equivalent expression. On page 237, it shows all of the identities that you can use to help you to basically you're transforming the expression to look exactly like the other side. So you want to change the appearance of the expression to something that is equivalent to that expression. Anyway, take a look at page 237. Those are all of the identities that are of use to you in this section. I'm going to go through a couple of examples with you. I encourage you to read the examples that start on page 238. There's 4 good examples. The key concepts explain to you techniques for solving trig identities. But for now, we'll just try and figure one out, I guess. Let's turn to page 240. I'll give you some strategies that I use when I'm solving trig identities. I find them actually kind of fun. They're interesting because they're like a puzzle. You're trying to change the appearance. You're trying to work with the identities that you have to try and make them look like the other side. So if you like any kind of puzzles, this section is for you. So here's the question that we're starting with. Sine of x plus pi is equal to negative sine x. So notice on the right-hand side of this expression or this equation, there's nothing you can really do with it. You can't turn sine x into anything else. So I guess you could turn it into 1 over cosecant x because that's its reciprocal, but you wouldn't want to do that. On the left-hand side, we have a compound angle formula. We have sine of x plus pi. So I'm going to work with the left-hand side, and I'm going to try and change the left-hand side into something that looks like negative sine x. All right, so I have an addition formula for sine. So you can flip back to page 237 and see that the sine of x plus y is the sine of x plus the sine of y, times the sine of y, and in this case y is pi, plus cosine x times the cosine of y, and in this case again it's pi. If we aren't allowed to use calculators, or I discourage it, that's for sure, then we have to figure out what the sine of pi is. Well, there's 2 ways we can find out what the sine of pi is. We can think back to our unit circle, and everything on that unit circle, we said a point P on that unit circle had an x coordinate as of cos, let's say it's theta, this angle's in standard position, and then sine theta, and that angle's in standard position. So cosine comes first, sine comes second, x, y. Well, pi happens to be an angle in standard position as well. It extends all the way over to here, to the x-axis. If we're talking about a unit circle, that means the radius of this circle is 1, and therefore the coordinates of this point would be negative 1, 0. Well, the -1 would be representative of cosine pi, and the 0 would be representative of what the sine of pi is. Okay, so really we can see what the sine of pi is. It's 0. So we can substitute that into the left side where we have sine pi. The other way that you can look at sine pi, I always prefer this method better, but some of you are pretty inept with the unit circle, so I'll show that first. You know the sine function goes like this. There are 5 major points on the sine curve. Okay, the 5 major points. That one's getting a little tight there, but well, the one we're looking for is right here, the sine of pi. We can see that the sine of pi is 0 because that's where it crosses the x-axis. So there's the 2 different ways to find out what sine of pi is. Or the cosine of pi, you just draw the cos graph. In any case, so what we have here then is left side is that, so we're going to just fix this up a little bit. Sine x, can't really do anything with that, but the sine of pi we just determined is 0 without using a calculator. And we just determined that the cos of pi is -1. We use the unit circle for that one, which is you know, a little bit different than the graph itself. And now I just decided that I've drawn this equation wrong. So I'm going to fix it. Sorry about that. The sine formula actually is sine x cos y. So in this case, cos pi plus the cos of x and the sine of pi. And you can see that for yourself if you flip back to page 237. So now I've done the calculations already for cos pi, which I see is -1. And I've done the calculation for sine pi, which I see as 0. So the first term would turn into negative sine x, and the second term would turn into 0 because anything times 0 is 0, and therefore I get negative sine x in return, which in fact is equal to the right side. So this strategy of solving left side equals right side, you notice at the end I didn't have to do anything with the right side, so I just made the left side look like the right side. The steps that I've carried out, it looks like, yes, I could have skipped some steps, but just note that skipping steps in trig identities is strongly discouraged because I need to see everything that is in your thought process. And the reason being is that you already know what the answer is supposed to be, negative sine x. So at any point in this solution that you're carrying out, you could just write, you know, right from this step, negative sine x. Even though, like, you can kind of see that it's supposed to be negative sine x, it's very important that you show me the first term was negative sine x, the second term was 0, therefore the whole thing is negative sine x, because for that very reason, because you know what the answer is. You could just write down the answer at any time when you get stuck and think, oh, okay, I'll try and fool them that I know the answer. I'll write down a bunch of gibberish. Okay, doesn't work. So make sure that you carry out those steps properly. Okay, let's tackle number 8. It says to prove, and here we have left side and right side. Left side only has a sine x in it, +1, so there's nothing really we can do with that. So we will begin on the right-hand side. A strategy for any of these trig identities is to look at the terms or the side that doesn't have a sine or a cos in it. So in this case, we have this cosecant x. Your eyes should be directed there because there are identities that turn cosecant x and anything that's not sine and cos into sine and cos. So that's your first strategy. So my first strategy here is to work with the right side and get everything turned into sine and or cos. So I'm going to use the reciprocal identity, and I'm going to turn cosecant x into 1 over sine x. Now I have something that I can work with. I can actually carry out an addition here. I have 1 plus 1 over sine x. Okay, I can turn two terms into one term by getting a common denominator. I'm going to turn the 1 into sine x over sine x, so I have a common denominator. See, it gives me something to work with. Now I've got something here that I'm adding together. I have my two numerators, sine x plus 1. I have my common denominator. I only have to write that once. And there. Now I'm at a point where, okay, I've added my two terms together. I got a common denominator, and then I refocus on what I'm supposed to look for. I always encourage you to go back and look at the other side. What are you trying to make it look like? Well, you're trying to make this look like 1 plus sine x. And I already have a 1 plus sine x, but I have these other two pieces in my way. But I do know that these two pieces actually cross out, right? I'll show you why they cross out, of course, because when you multiply fractions, this is over an invisible 1. So really I have sine x times sine x plus 1 over sine x. So yes, of course they cancel out because they are like factors. Now that we are multiplying, you can see we're multiplying because of the bracket there. Now that we're multiplying, we can cancel those out. And therefore, I'm left with sine x plus 1, which is the exact same as the left side. Okay, so like in the other example that I showed you, you can't skip any steps. Okay, it's very important. You see that I've shown, well, actually you could have skipped this step here because I canceled out in red the sine x's in the step just before that. So I'm showing that I'm canceling those out. I didn't just simply jump from this line to this line without actually showing that I've canceled out the sine x's. I have to prove knowledge. If I can't prove knowledge, then I'm not going to give you full marks for a solution. Okay, we'll look at some of the ones that have the Pythagorean relationships. So you have the exponent 2 in some of these trig ratios. Told you the strategy that I like using, and that is to change everything into sine and cos. And right now we have nothing in terms of sine and cos. So we could look at, say, the left-hand side and show that the left-hand side, here's a unique situation. We know that, I'll work off to the side here for 1 second. We know that cosecant x is a reciprocal of sine x. Okay? So we have that identity. But it also allows us to, if we want to, we can square both sides of this identity, which suggests then that cosecant squared x is the same as 1 squared, which is 1, over sine squared, which is sine squared x. So the reciprocal identities also work when they are squared. Okay, so on the left-hand side then, we actually have cosecant squared x, so that is the same as 1 over sine squared x. And now that it's in terms of sine, I'm happy. I can now work with the right-hand side. I can go back and work more with the left-hand side if I want to, but I'm in terms of sine right now, so sine gives me happiness, which means I can stop there and be pretty satisfied. I don't have to change sine squared into 1 minus cos squared. I don't have to do anything like that because it's already in terms of sine. Right-hand side is not. So I'm going to jump there, and I'm going to change cotan squared into 1 over tan squared. Okay, using the reciprocal identity and the fact that I can square both sides of that identity makes this true. Now, whenever I have two terms and only one term on the left side, I want to turn the two terms in the right side into 1. So I have to add these two fractions together so I can make the 1 into a tan squared x over a tan squared x. And then I have still the 1 over tan squared x. Now that I have a common denominator, I can write the denominator once, my common one, and add my numerator together. Okay. Not sure that that really helped me too much, because now I just have a bunch of tans on the right hand side. Doesn't really get me any closer to where I want to go. So what I can do is I can work with the identity. Oh, I just thought of something. I probably should have just jumped into the identity on page 237 and used the same idea with these red brackets up to the right hand side. It says the quotient identity is tan x equals sine x over cos x. Right? Which would be true if I squared both sides as well. Then I'd have tan squared x, and I square the right hand side too, which means I have to square numerator and denominator. And if if cotan and tan are reciprocals of each other, that would mean then that cotan squared is the same as the reciprocal of the right hand side for tan. So that's what I could have used, and then I jumped directly to sine and cos, which is my original strategy. Okay. In any case, I will continue with the right hand side over here just to show you that that is true. Tan squared is the same as sine squared x over cos squared x. So I can show you that sometimes when you get off on a tangent, you can still get back into focus. It just means you're doing maybe a little bit more work than the person beside you. So I've turned tan squared x into sine squared x and cos squared x. And now I can get a common denominator in the numerator. You can see, I'll just do it in red here, that 1 is the same as cos squared x over cos squared x. I want to do that because I want a common denominator with this fraction. So my numerator would look like this: sine squared x plus cos squared x. Those are my two numerators in the numerator. My common denominator is cos squared x, and then that is all over sine squared x over cos squared x. There's a Pythagorean identity that says sine squared x plus cos squared x equals 1. So I will write it as 1. Okay, so I'm just showing you that this one here equals 1. It still gets written over cos squared x. I'm going to show you another thing. This fraction symbol, any fraction symbol, is just a division statement, right? So I'm going to just write it as a division statement instead of a fraction, because I want to actually divide these. I can divide these by simply changing the division sign into a multiplication sign. It's called invert and multiply. Invert your second fraction, change the division to multiplication. And now I can see that this co-squared and this co-squared cancel each other out, and I'm left with, oops, I didn't mean to turn to red here, but that's fine, sine 1 over sine squared x, which if I look above is what the other side, what other side was that? The left side. Things are sliding all over the place. Which is equal to the left side. Okay, so like I said, always try and my solution is correct. It's long, but it's correct. And notice that I could have made it a lot shorter if I had just utilized the fact that cotan squared is the same as cos squared over sine squared, and substituted that in pretty much right away. Okay, right where I did that step. Okay, because the right hand side had a cotan